So the quiz on Thursday will be showing that a limit doesn't exist and then finding some partial derivatives. Okay? So our first task is to look at some higher order derivatives and then apply this, this theorem, an interesting theorem for nice continuous functions that will be useful for us sometime in the future. So if we recall some of the derivatives that we were working out, the notation that we had for the derivatives that we saw yesterday was fx, which is a partial of f with respect to x, and fy, partial of f with respect to y. And so this is our first order derivatives, we can call them, for functions where you have f that goes from R2 to R. And what we want to do is we want to explore some higher order derivatives. So let's take a look at how higher order derivatives work and then find the notation, find a good notation for it. So higher order derivatives would be like the second derivative, third derivatives, and stuff like that. So what we want to do is we want to take the derivative of something with respect to something else. So let's take a look at the notation first. If we have f sub x, this is the first derivative with respect to x. So this is a function already. Maybe we should do an example at the same time, and let's do an example where we have f of x or f of xy equals x squared minus 2xy plus y to the third. So the first derivative that we can consider, we could consider is the derivative with respect to x. So let's see what this is equal to. This is 2x minus 2y, and then the last component 0. Right? So that's our first derivative. Now fx in turn is actually a function. Oops, trying to move this over a little bit. This is actually a function of x and y also, right? So if we have a function of x and y, then we can potentially take the derivative with respect to x or with respect to y. So one of our possible derivatives from your derivative is to take the derivative of the derivative with respect to x again. So it's like taking the derivative of fx with respect to x. So actually the notation for this is fxx, to say we're going to take the derivative with respect to x and then with respect to x again. And what does that look like? Well, you take fx and you take the derivative of fx with respect to x, so that's just going to be what? That's just going to be 2. What happened to this? There's something happened here. Oh, my y didn't get moved. There it goes. So fxx is equal to 2. Right? That's straightforward enough. If we find fy, the result will eventually also be a function of x and y. The derivative of that is 0 minus 2x plus 3y squared. So fyy, we can take a look at that in two steps. First, we need to take the derivative of fy, or we need to take the derivative of f with respect to y, and then take the derivative with respect to y again. And so we took the derivative with respect to y, take it with respect to y again, we're going to get 6y, positive 6y. Right? So is that all the second order derivatives?
Couldn't you take one with respect to y and then another with respect to x?
So remember that fx is a function of x and y, and we only took the derivative with respect to x. We can potentially also take the derivative with respect to y. So if we take fx and then in turn take the derivative of that with respect to y now, then that's different from the other ones that we've done so far. Right? So let's take a look at that. That's fx over here. We want to take the derivative of this with respect to y. So what's the derivative of this with respect to y? Negative 2. And that's different from the other two derivatives that we found. Are there any other derivatives we could take? Fyx. So fyx is actually equal to fy, and then that fy function, you take the derivative of that with respect to x. What is that equal to? Negative 2.
So it's going to be the same, like, regardless.
Is it?
Whenever you take like a function f with respect to x or with respect to y and vice versa, you always end up with the same.
You think so? All right, well, let's explore it with a couple more examples, but it looks like these are different from each other, and these are the same. So we asked, is it a coincidence or not? So let's mess around with a few more different functions and see if it actually will remain the same or actually be different. Let me talk a little bit about notation first. So it's easy for us to think about fxx as taking the derivative with respect to x and then taking the derivative again with respect to x. So I don't know if you guys remember the Leibniz notation and where the square thing goes, right? So d squared x or d squared f divided by dx squared is really the thing to do, because what's really happening here is that you're taking the derivative of f with respect to x, and then after that you're taking the derivative of this with respect to x again. So you're kind of like, this is a little bit of an abusive notation, but we're thinking about the dx as one term, and then you're thinking about the operator d as a separate term, and the f really only happens once. And so that's how, we don't say df squared over dx squared. That's not proper notation. That's not how we write the second order derivative. So the d squared happens here. Okay? So sometimes you might see this notation. This is why we're doing this. Most of the time, like I said, the fx is easy to write, so fxx seems easy to write, natural and easy to write. So fyy works the same way, but let's take a look at fxy. So fxy says that we're taking the derivative of f with respect to what first? With respect to x first, right? And then after we take the derivative with respect to x, we're going to dy it. We're going to take the derivative of that with respect to y. Now, if you look at how this notation works, when we put it together, this will give us a d squared f, and then this is dy dx. So look at this. fxy d squared f dy dx. Look at the placement of the x's and y's. Okay? So in Leibniz notation, when you see partial derivatives, it's kind of written from right to left. You're taking the derivative from right to left, x first and then y. Now that's certainly going to make a difference if the fxy and fyx are not always equal to each other. And like I said, we're going to explore that in a few minutes, but we have to be careful when you're switching from the Leibniz notation to the subscript notation that your corresponding derivatives are going to be the same. All right? So here's the summary of it. That's not it. Here are for functions that go from R2 to R, here are the only 4 possibilities of the second order partial derivatives. So this isn't all the higher derivatives, this is just a second order. Partial derivatives. There's 4 of them. So fxx, fyy, written simply as that, and then fxy and fyx. These two have a special name. These are called mixed partials. Let me rewrite that better. Mixed partials. Because you're mixing the variables x first and then y, y and then x, and there's 2 of them. So sometimes they might ask you for the mixed partial derivatives, and then you would do the second order partial derivatives, one variable first and then the other variable second. All right? So now let's check, let's do another example. Let me see if any of these look. I don't know. Pick a number between 53 and 58. 53? Oh, that one's easy. 56. Oh, that one's a... All right, let's do that. $56 requires the quotient rule, so... All right, so our function is called v now instead of f. So let's be flexible. Let's call it v sub x, the derivative of v with respect to x. And it looks like there's an x both in the numerator and denominator, so I'm going to need to use a quotient rule. And since I'm going to go second derivative, after I take the derivative, I probably want to simplify it, so I'll be ready to take the second derivative. Low d high, high d low, low squared. So low x minus y, the derivative of the high. The derivative of xy with respect to x, y is a constant, so derivative of 5x is 5, so that's like y. Minus high d low, high, the derivative of low with respect to x is just 1, or 1 minus 0, and then we divide by low squared, xy quantity squared. So I can go with this, or I could try to simplify it a little bit. I have xy minus y squared minus xy. So the xy's look like they might cancel, and they have a negative y squared up on top. So my result here is minus y squared divided by x minus y quantity squared. Did I do that right? All right? Let's say yes. Let's try to do the second one, Vy. Okay. Same thing, except we're taking the derivative with respect to y. So low d high minus high d low divided by low squared. Let's do some simplifying again. We have xy minus, or x squared. Which one's positive? Oh. So x squared minus xy minus positive xy. So they still cancel. The xy's still cancel. That's good. And so we have just a positive x squared divided by x minus y quantity squared. Yeah? Because the derivative of the denominator with respect to y. So the derivative of the denominator with respect to x is 0, minus the derivative of this with respect to y is 1. There's a negative sign there. So low d high minus high d low, the derivative of the low. Okay? You all write it down. Low d high d low, low square. Any way you want to remember your, that's how I remember my quotient rule. You remember it any way you want, but I'm expecting you to know it because you guys are big now. What? You could use the product rule if you want, then you're dealing with negative exponents. So if you're fine with that, but if you're fine with that, that's fine. All right, let's move on. Remember, that's a prerequisite for this class. You guys have to know the quotient rule. Well, that's the quotient rule. All right, so that's Vx and Vy. So now let's take a look at the mixed partials. I mean, you could compute the Vxx, Vyy, but I'm not too concerned about that. I'm more concerned about the mixed partial derivatives. So let's take a look at Vxy. So which one do we look at, Vx or Vy? We look at Vx and we take the derivative of this with respect to y, right? So there's a couple ways to denote this. I can use the curly D, or I can just write, I'm going to write it like this so I can have it right next to me as I'm taking the derivative of it. So I'm going to rewrite the whole thing. This is Vx. And I'm going to say I want to take the derivative of this with respect to y, and I'll do a little subscript on the outside brackets to say I want to take the derivative of that with respect to y. So, taking the derivative of this with respect to y, there's a y in the top and there's a y in the bottom, so I'm going to need to use a quotient rule again. So low d high minus high d low. Low d high, the derivative of this is negative 2y to the first power. I guess I can use regular parentheses. So low d high minus high d low. The derivative of low, I need brackets because I'm going to use the power rule. 2x minus y to the first power times the derivative of the inside with respect to y, which is negative 1. So low d high minus high d low all over low squared. So that's x minus y quantity to the fourth power, or squared and then squared after that. So you multiply the powers. Okay? You could do a lot of distributing, but So I could just leave it like this, but I'm in a process of comparing it to the other one, so let's do some algebra to simplify it. And the way I'm going to do my algebra is that I'm kind of seeing the x minus y happening in the two terms up on top, so I can think about factoring that out and just canceling with one of the x minus y's in the bottom. Yeah?
How did you get the x minus y from the quotient?
It's the low squared, so x minus y squared squared. So low d high minus high d low divided by low squared. So the low is x minus y squared, and I'm squaring that. Okay? I don't think that's tricky. I think that's just Calc 1. Well, I mean, well, like I said, any way you get there, just get there. I don't really care how you take the derivative of a quotient. If you want to make a product rule out of it, that's fine with me, as long as we're getting the same answer. Okay. All right. So here I'm going to pull some algebra magic here. I'm going to take away this x minus y from both of these. So that gets rid of one of them. That gets rid of this one. Just so I can cancel with an x minus y in the bottom. So I got the x minus y. So what do we have left on top? I have an x minus y to the first power after I got rid of this one, times negative 2. I probably still want to simplify that, times negative 2y, minus, and in this term, I got a negative y squared times 2 times 1 times negative 1. And I suppose we can still work on this to simplify it. But my first... Yeah, so we're going to continue to work on that. But here, this first step is just to get rid of one of these x minus y's. And then let's continue to simplify this. And then I'll write up what's going on up here. I have a negative 2x times y. Negative negative is a positive 2. Y squared. And then here I have a negative, and a negative negative is a positive. So that's just negative times a negative times a negative will end up being negative, and then a 2y squared. And so I think I'm going to be able to cancel the 2y squareds. And so this is all I would have left in the numerator. Negative 2xy divided by x minus y to the third. So this is vxy. All right? So there was just a little bit of calculus and a little bit of algebra involved there. Or, okay, a lot of calculus and a lot of algebra. But we got a simplified answer. And now let's find the other one to see how it compares. So the other one is a vyx. That's your other mixed partial. So it's x squared, x minus y quantity squared, and then we want to take the derivative of this with respect to x. So I'll switch notation here and say the partial with respect to x of this thing. So I'll use the partial notation for this. But we're really looking for the same thing here. Now we're going to treat this Vy function as a function and then take the derivative of this function with respect to x. So clearly it's an x on top, x in the bottom, another quotient rule. So low d high. So low d high minus high d low. The derivative of low is another power rule. So the derivative of low is 2x minus y to the first power times the derivative of the inside, which is x. The derivative of x with respect to x is just 1. All over low squared, and then so that's the x minus y squared squared again. And I see that same x minus y that matches the x minus y factor in the bottom, so I can factor that out again. So let's do that. So if I factor out an x minus y, I'm going to get an x minus y to the first power, because I factored one of those out. And then I have an x squared times 2 times x minus y, which I factored out, times 1. So this is my whole numerator. And then this will allow me to cancel one of my x minus y's on top with one of the 4x minus y's in the bottom. That will leave me with x minus y to the third. So let's see how this simplifies. Let's multiply this out. I'm going to get 2x squared minus 2xy minus 2x squared. So I got negative 2xy. So this is equal to negative 2xy, x minus y to the third. This is our Vyx compared to Vxy, and look, it looks the same. Coincidence? I think not. Okay, so that was fun. So that leads us to this theorem that says if you have a function that's nice and continuous around a certain point, then all the other points near that point would satisfy the condition that the mixed partial derivatives are equal. Fx equals Fy, or Fxy equals Fyx for those values. And this idea will be useful for us in the future. So it's good to know that the mixed order partial derivatives are equal for a lot of these functions that we're going to be dealing with. So in math, they usually find exceptions for things. So there's, we can find non-continuous functions, usually when the denominator is equal to 0, where this won't work. But we're more interested where this actually works, and this works for about 99.9% of the functions that we're going to be dealing with. Maybe 100. All right. I was looking at my notes, and I noticed that there was also some interesting graphical ideas for determining the rates of change. And so let's take a look at a level curve. Do you guys remember what level curves are? Or contour plots. You guys remember what contour plots are? That doesn't help. If you take a look at a surface and you cut it with horizontal planes and look at the shadow, think about a contour map. If you're looking at a map of a mountain and then they have these lines.
Actually, for example, Contourplot is mapped with actual height. For example, I deal with it literally every day now.
Yeah? Should take screenshots of it and then so we can show it to the class. Yeah, maps. A lot of maps have them, especially the hiking maps. So you know when you're going up higher and lower. All right, let's see how we can apply this idea of a contour map and finding derivatives. Now, we did a table. We did a table of the wind chill factor, and then from the table we found estimates for finding for getting the derivative with respect to x and with respect to y. And so now what we're going to do is we're going to take a look at a contour map that's labeled so we know the different contours. So let's say you're on the side of the mountain, and currently you're about I don't know, we call it 6 or 600 feet above sea level. We can think about the 6 as that. And then depending on which way you go east or north or west or south. Did I do that right? Then your elevation will change according to the direction that you're going to move. So north, east, south, west. So this is our map. So let's take a look at see if we can find whether it's positive, things are positive or negative. Let's take a look at fx first of all. Fx tells us from this point we want to move in the x direction. Which way in your map is the x direction? Going west. Oh, so let's go in the positive. Usually when we think of the rate of change, we're going in the positive direction. So positive x is what? East. Positive x is east. So let's imagine.
Your cardinal directions are wrong.
Are they?
Yeah, west is always on the right. Oh, sorry, never mind. Sorry.
Okay. This is right, right? All right. So here we're going to move this way. So what can you say about the sign of this? Does this look like if we're in the map and our map tells us to go east and we're standing on point P, which is about 6 feet above sea level, if we start taking steps east, are we going to go up or down? We're going to go down, right? We're going to go from level 6 to somewhere level 5 and level 4, eventually get to level 4 if we walk this far. So we're going downward, so is this positive or negative? Negative. So this is a negative value, so the value of fx should be less than 0 at that point P. So now let's take a look at fy. Fy is north, right? Positive. Positive y direction is north. So now if you move up north, are you going to go up or down on this mountain? You're going to go from level 6 to level 8, right? So you're going to be moving up. Okay? All right, so now it gets a little trickier. And let's try to interpret this as the rate of change in height with respect to the rate of change of the rate of change of height. So we know that the rate of change is going down. It's going down, right? But what is the rate of change of x as we keep moving in the x direction? So the tricky part is what you have to look at is are the distances between the level curves. So if we go this way farther, we have a small change, and then we go to a larger change. So does it look like it's increasing? So the number's going down, so that's the fx part. We got that this is negative. But then as you go down, how should we put it? As you're going down the hill, it's getting less steep. So is the hill going to be shaped this way, or is the hill going to be shaped this way? Which one's the second one? Is it 1 or 2? Have you guys been eye doctor lately? Do you prefer 1 or 2? 1 or 2. So it's the top one. So it's decreasing, right? But the rate of change of decrease is positive. So it's really a question of concavity, right? And in this case, it looks like if you go in this way, it's concave up. And so concave up, we usually think about positive or negative? Positive. So fxx is going to be positive. So let's take a look at fyy. So this one's kind of like the same idea. You're going up this way, and then the first few steps, there's a longer gap, and then it's shorter and shorter. So I know that I'm increasing, so I'm ready to draw that my graph is going to go upward. So the question is, which one is it? Is it 1 or 2? So is it 1 or 2? It's 1, right? It goes up kind of slowly, and then it starts going faster and faster. So it'll be this one. Say it again? Yeah, we're starting from P, from point P. So this is concave up or down? This is concave up again. All right, fxy. How's that going to go? I forgot how this goes now. Now let's just skip it. I hope you guys don't have any homework problems with it. Let me think. No, I can't think of anything. How's it go? Yeah, I was just thinking about skipping it. Danny, what's up? So the rate of change, so at first it's going positive. We know that it's going to go from 6 to 8 to 10 if we go in the y direction. Now, so as we move in the y direction, the difference from level 6 to level 8 is kind of far away. But then the difference from level 8 to level 10 is shorter. So it goes up slowly, and then it goes up faster and faster. And so we can see the concave up shape out of this out of this drawing. Well, not that you're going up at an angle, you're going up at a slope, and then your slope is changing and getting steeper and steeper. So when your slope is changing, getting steeper and steeper, it gets steeper faster, then you're looking at something that's concave up. Well, you're going in the north direction, and as you're going in the north direction, you're moving up. This is the shape of the graph that you're going. No, because you're going FYY, so it's just going in the north direction. So you're going in the north direction, you're increasing. Oh, yeah, so that one, that's the one I couldn't really figure out. You're not going in a 45-degree angle, I think, I'm not sure, which is why I don't want to present this, but let's see. My guess is that your fx, how is your fx changing as you move up along the y direction? And so I think this is a drawing we want to look at, and we want to look at what the distances are from the level curves. Is it how it's changing? And I'm not, that's why I'm not kind of seeing the picture, so I don't want to talk much about it anymore.
It's kind of like, yeah, it's kind of like, I guess you're moving up the hill, but like, not exactly, but like a diagonal.
No, so I don't want to say diagonal, because I don't think it's diagonal. Yeah. All right, let's skip over that and not worry about it. Let's see. There are some interesting applications that I saw that I thought maybe we should go over. I don't know if we're going to have time to talk about 14.4. All right, well. All right, let's spend some time on this. I think we're going to fall a day behind, but it's not bad. That's okay. Which one should we do? Let's do some of number 76, and then we'll do 81, and we'll see if we have time. We'll do 83 also. So in Calc 2, when you first started learning about integrals, they presented this idea of a differential equation, and the way you guys can solve for differential equation is usually just to integrate. Those differential equations that you might have seen, if you remember seeing them, actually the acceleration to velocity to position, that's also an easy type of differential equation, because you have a derivative of a function and then you integrate to find the original function, and that's how you eventually get the position function. In this example here, we have derivatives, but we have not just derivatives, we have partial derivatives. So those regular derivatives with the position to the velocity from the acceleration to the velocity to the position, that's called ordinary differential equation, because your differential equations are just dealing with derivatives of regular one variable functions. But if you get a derivative of a function with several variables involved, now we have what's called a partial differential equation. So a partial differential equation is an equation that has partial derivatives, and usually your task is to find the original function. Now, our task of finding the original function would be kind of difficult at this level. So what they do in these problems is that they give you possible solutions to see if they actually satisfy the differential equation. And the way to deal with this is that if this is the differential equation, this is the partial differential equation, PDE, so if this is your partial differential equation, and let's say one of these is a solution to your partial differential equation, then you could take the derivative of this according to what they say in the PDE and then plug it into here to see if it'll satisfy that equation. Just like, you know, x plus 1 is equal to 0, and you say, what, is the solution x is equal to 2? How would you check? You would put 2 in here to see if you get this to equal, right? And then you could put 2 in there and say, oh, that doesn't work. Is 1 a solution? Is negative 1 a solution? So if you put negative 1 in here and it does work, you say, oh, yeah, that is a solution. So that's kind of like the same idea, is that you have your equation, you have your solution, you want to check to see if your solution works. So let's check if this u is equal to x cubed plus 3xy squared is a solution for this partial differential equation. So what do we need? We need u sub x, x, and u sub y, y, right? So let's find that for this problem. So u sub x, we need to do this in pieces because we need to figure this out. So u sub x is going to be, with respect to x, 3x squared plus 3y squared, right? And then we need u sub xx, so we'll take the derivative of this since we have it here already. Take the derivative of this again with respect to x. That looks like it's just going to be 6x. So now let's take the derivative of u with respect to y, and then take the derivative with respect to y again. So u with respect to y is going to be 0 plus, this looks like it's going to be 6xy. And then take the derivative of this with respect to y, it's just going to be 6x. So now the question is, if we plug in uxx and uyy into this equation, are we going to get 0? 6x plus 6x equal to 0. And the answer is no. So this is not a solution to the partial differential equation. All right, so the function's not a solution. Let's try another simple one. Let's try b. So u is equal to x squared minus y squared. Let's see if that works. We need ux. That's 2x. Just 2x. uxx. That's 2. Wait, let's find the uy first. Uy is going to be negative 2y. Uyy is going to be negative 2. So we take the uxx and uyy and add them, and we get 0. Yes. So we could say, yes, this is a solution. So this is a solution to the partial differential equation. Okay? So it's a matter of taking derivatives to figure out if this will work out. All right, let's do one more. of these applications. Number 8 is another partial differential equation problem where you want to check if something's a solution. So we'll skip over that. Let's do number 83. These things have resistors that you guys might run into in some of your circuits class or whatever. And for this problem, all they want us to find is dr, dr1. So r is your function, and it's a function of r1, r2, r3. So essentially x, y, z, it's a function of 3 variables, and instead of x, y, z, they use r1, r2, r3. So r1, r2, r3 are the independent variables. The dependent variable is r. Now, we have an unfortunate situation here in that r looks like it's in the denominator or something. So one way to deal with this is to solve for r, taking the reciprocal. And you can't just say r1 plus r2 plus r3. No, that's not how that works. You have to find common denominators and then take the reciprocal. So that might be a little bit more complicated than what it's worth. And so the other way to do this is to what? Any ideas? If I want to find the derivative of capital R with respect to little r, or with respect to r1, and capital R is not explicitly solved for by itself, there's my hint, what do? Implicit differentiation. It's not explicitly solved, so let's differentiate implicitly. Okay, so let's do implicit differentiation. We want to find dr, dr1, and we're going to assume that r is this function of x, y, z, or r1, r2, r3. So whenever we touch r1, or whenever we deal with r, we're going to assume it's a function, so we're going to induce some sort of some chain rule business. All right? So let's rewrite this as, maybe this might help a little bit. R to the negative 1 is equal to R1 to the negative 1 plus R2 to the negative 1 plus R3 to the negative 1. Again, just to let you know, this is not R is equal to R1 plus R2 plus R3. You can't just take reciprocals of things that you're adding and subtracting if you're adding and subtracting them separately. So this is bad, 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 bad. It's just algebra, but it's a common mistake, so please be careful with that. All right. I want to take the derivative with respect to r, so I'll say d, oops, I don't want a straight d, right? I want a partial d. So I'm going to treat r1 as my x, the variable. R2 and r3 are constants in this scenario. So the derivative of this is negative 1, r to the negative 2. Since r is a function of r1 and also r2, r3, we want to take the derivative of that, r, with respect to the r variable that you're going to take the derivative with respect to. So that's the whole left-hand side. That's like the quotient, that's like the power rule. Negative 1, r to the negative 2, and then take the derivative of the inside, take the derivative of r. Now, this is the independent variable, so that's negative 1, r1 to the negative 2. And if you want to think about this, you're taking the derivative of this with respect to r1, so this is dr1 over dr1, which is equal to 1. What's the derivative of this with respect to r1? So these are the independent variables, right? So this is like R1 is like the x, R2 is like the y. So the derivative of y to the negative 1 with respect to x is what? It's a constant. So it's 0. And then the other one's 0 as well. So really you just have to solve for this. This is what you're looking for. And so we'll bring everything over to the other side by dividing, it looks like, and then I can cancel out the negative 1s because they're both negative 1. So the partial of r with respect to r1 is going to equal to, I'll write it like this first, and then I'll use some exponent rules and stuff, and that's just going to switch the order. Or r over r1 squared. So the rate of change of the resistor with respect to the first r1 variable is equal to this. Okay? All right, there's a lot to think about, I'm sure. So tomorrow there's no classes because it's flex day. And I will extend 14.4 by 1 day. Was it due tonight? Oh, it's due tomorrow anyways. So I won't extend it. Because you need to do it before Thursday. Thursday we're going to go over 14.4. The lab, yeah. So we're going to go over 14.4 on Thursday. I think that's it. Not yet. I'll see you on Thursday.